Good evening, everyone. I'm Calvin Joseph, and today I'm going to conduct the summary session for the course State-Space Approach to Control System Analysis and Design, just taught by Professor A.P. Tiwari of IIT Mandi. So, the objective of this session is to provide a recap of the entire course such that it will help you for your exam preparation. Okay. So, in the week one, what have we considered the mathematical modeling of systems, the series RLC system, and the op-amp filters, and various the advanced mechanical and electrical systems were considered. Their mathematical models were developed. Okay. So, for the summary session, so week one was the preliminary lecture where the focus was on mathematical model development. Where actually what you are supposed to do is you have to derive the differential equations governing the hold on 1 minute. So you have to derive the differential equations governing the behavior of the system. Okay. So like you're doing sort of root cause analysis, or you're like building the model using first principles. You will be using laws such as laws of energy conservation, law of conservation of momentum, or KCL, KVL, etc. All these laws you will be using to derive, and those are like the first principles which are governing the behavior of the system. And using those laws, you will find out what are the differential equations governing this behavior of that system. And that is your mathematical model. After that, what we will do, you will see in week two. Okay. Then in week two, we will do state space representation. So let us consider a linear time invariant system. So we represent the states as x dot t is equal to a into x of t plus b into u of t, and y of t is equal to c into x of t plus d into u of t. Okay. So this is the mathematical model of the system which is represented in state space form. Okay. So these are, linear first order differential equations. We have to select the states in such a manner that we get a linear first order differential equations we get. Okay, so one more point is this state space representation is not unique. It is not unique. There can be various states. So it depends on the choice of states. Okay, but the overall transfer function remains the same irrespective of the state selected. Okay, so transfer function is unique, but you can have different state space representations. So you'll have different ABCD matrices, etc. And now let us say we have X and we have to convert it using a transformation matrix to TZ. Okay, so then we will have a Z dot T is A Z T let us see, this is A Z Z T plus B Z U T Y of T is C Z Z T plus D Z U of T. So how do we get it this? We have to do. So we have x dot of t is a into x of t plus b into u of t. We will put t into z dot of t is a into t into z of t plus b into ut. Therefore, z dot of t is equal to t inverse a t z of t plus t inverse b of u of t. So we get z dot of t is equal to a z of t plus bz u of t. So az actually is equal to t inverse at and bz is actually t inverse b. Okay, similarly you will get cz actually is equal to c into t and dz remains as it is. Dz is equal to t. Okay, so that is how our state space representation, that is our a b c d, gets converted from x equal to tz into the form of az bz cz dz. Okay, so this is the transformation from one state space representation to another state space representation. Then there are various canonical forms. You have first companion form, then you have your second companion form, then you have what is known as your Jordan form. So the Jordan form is the one which you will get by using partial fractions. So it is a sort of a parallel representation of the states. And in case of repeated eigenvalues, you will have to have a different, there'll be a slight increase in the complexity. Slight complexity you will face. Okay, and each of these companion forms or these canonical forms have a characteristic way in which that A matrix, B matrix, C matrix will look like. Okay, so once you study these matrices, you can look at the transfer function, and from the transfer function, you can convert it into the first canonical form, first companion form, second companion form, or the Jordan form. Jordan form, you need to know the eigenvalues, etc. Okay. So, okay. Next is week 3. Week 3, which is been mainly related with the state transition matrix. STM. This state transition matrix for a linear time invariant system is given by e raised to a into t. E raised to a into t. And this has various properties such as, and this is represented phi of t. Okay. See, phi of 0 is actually an identity matrix. And if we need to find phi of t, this is e to power at, which is actually equal to I plus a t plus a square t square upon 2 factorial plus a cube t cube from 3 factorial plus dot dot dot. Okay, this is the phi of t, right? So it looks complicated. How will you do a square, a cube, a raised to 4? It is very time consuming. So there's a simpler way. What you have to do is you just have to do si minus a. So this is S into the identity matrix 1 0 0 1 1 1 0 0 0 0 0 etc. minus the A matrix. Okay. This will be size n cross n. This also size n cross n. Okay. Once you get Si minus A, you find the Si minus A inverse. Okay. Suppose this is sum. So this is actually 1 upon Si minus A. And then when you take the Laplace inverse, it actually will be e to the power at. So in this method, you can get e to the power at. You can get this e to the power at, which is actually equal to your state transition matrix. So this is the method I would recommend for someone. If they ask in the exam to find the state transition matrix, you can use this method. This is an easy method. Okay. So now let us see. Okay, further there's a discretization of LTI plant. So we have x dot t is a into x of t plus b into u of t, and y of t is equal to c into x of t. When you do discretization, you represent as x of n plus 1 is phi n xn plus gamma n un, and yn plus 1 is equal to c, yn is equal to c into xn. Okay. And a point to be noted is this phi n is actually e to the power a into t, and gamma n is integration of a to the power a tau b d tau, where it is changing from 0 to t. So you're discretizing the system with a time period t. So this time period t is important. This time period or this sampling period t determines what will be your effective discrete time equivalent transfer function of your system. Okay. Next, we'll go to week 4. So in week 4, there are the definitions of controllability and observability. So a simple way for us to determine controllability is to find the Q matrix, just given by B, A, B, A square B dot 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 A raised to n minus 1 B. So this is the Q matrix. This and the rank of Q should be equal to n for the system to be controllable. Okay. Now, if rank of Q is equal to m, which is less than n, then so there is a controllability subspace of dimension m, and there's an uncontrollability subspace of dimension n minus m. Okay. And one more point to be noted is if it turns out that m is less than n, so then the eigenvalues in the uncontrollability subspace cannot be altered. Okay, they cannot be altered. You cannot control, you cannot change their values using closed loop. So then what happens is if these eigenvalues, these uncontrollable eigenvalues, if they are stable, then what we can say that the system is stabilizable. So the system is not controllable now in this case, but the system is stabilizable. This happens only in the case when the uncontrollable modes, they are stable. So the uncontrollable modes are stable. We cannot, change those eigenvalues of the closed loop system, but we can make sure. But since they are stable, their dynamics will decay to zero as time t tends to infinity. But we will not get the response which we want always. But we can be rest assured that we can stabilize the system. Okay. Next is the concept of observability. And observability can be determined using the matrix P, that P actually C A squared, sorry, C A dot C A raised to n minus 1. This is the matrix P, which is your observability matrix. And similarly, as in the case for controllability matrix, what is the controllability subspace, what is the observability subspace can be found. And what does observability mean? It means using the measurement of inputs and outputs over some time, we can estimate the internal states of the system. So that's what it means. That is, I am observing the inputs and outputs, and I can estimate what are the internal states of my system. So it depends on which outputs we are measuring. And why observability is important is in all cases, we cannot observe all the states. So if we have some measurements of your input and the output, then we can estimate what are the internal states of the system. So this is used in observer-based design. So whenever we have to design an observer, we first have to check whether the system is observable. The system is not observable, there's no use of designing an observer, right? Next, we'll go to week 5. Okay. Week 5 is related to stability. So before we do all this, there are certain mathematical preliminaries. So there is set of mathematical preliminaries. One is you have a positive definite function. So you have to know what is a positive definite function, what is a semi-positive definite function, what is a negative definite function, etc., etc. Then what are quadratic forms? So let me give an example. That is, we have x1 square plus 4x1 x2 plus 8x2 square. This can be represented as 1, 2, 2, 4. Sorry. It can be represented like this. It's equal to x1, x2, 1, 2, 2, 4, x1, x2. Okay, so it is represented in the form of x transpose px. And you must make sure that p is symmetric. P has to be symmetric. Okay, that is why this 2 actually is equal to 4 by 2. So this is one quadratic form, and you can show that it can be positive definite, like this can be seen. We can understand the mathematical properties of that. So this is a quadratic form which you will be needing. And now we will consider for Lyapunov stability. We have to find the A transpose P plus PA should be equal to minus Q, where P is positive definite and there are certain conditions. Let's go week 5. Okay, one is stability is we can say that the poles are in the left half of the S plane. That is one definition of stability. And okay, where we consider stability in the neighborhood of the origin, we are considering a function v of x. So this v of x should be positive definite, and v of 0 is 0, and v of x should be greater than 0 when x is not at the origin. Then the derivative of x should be less than 0 when the point is not at the origin. Now global asymptotic stability. V of x is positive definite, v of 0 is 0, and v of x is greater than 0 for all x which is not equal to 0. And v of x tends to infinity as the norm of x tends to infinity. That is, v of x is radially unbounded, and v dot of x is less than or equal to 0, and v dot of capital X is not equal to 0 along any trajectory of the system except at the origin. Then we say that it is globally asymptotically stable. Now, in case v of x is greater than 0 and v dot of x is greater than 0, then this under these conditions the origin is said to be unstable. Okay. So we have v of x, v dot of x, we can find the range of stability. Okay. Then okay. So for a linear system, let us say x dot t is equal to a into x of t, we get v dot of x is equal to minus x transpose qx. So we should have this q equal to minus a transpose r plus ra. Okay. So here r is positive definite and q also must be positive semi-definite. So if v dot of x should be negative semi-definite, then q must be positive semi-definite. So we select a positive semi-definite matrix q, and then we find an r, and then we check whether that r is positive definite. If R comes as positive definite, then we can say the system is asymptotically stable. Okay, so one example was there. So let me change it. This actually is A transpose R plus RA is equal to minus Q, where we selected Q. This should be positive semi-definite. My R should come out to be positive definite. If this happens, then we can say that the linear time invariant system is globally asymptotically stable. Okay. So for nonlinear system, what happens is x dot is equal to f of x. We represent f of x using Taylor series expansion as f of x equal to f of 0 plus summation of I equal to 1 when dou f upon dou x of I, where x equal to 0 for xi and higher order terms. So since we are assuming that the origin is the equilibrium point and f of 0 is equal to 0, so we get f of x is equal to ax plus g into capital X. So g of x contains the second order and higher order term. So x dot is equal to a into x plus gx. Now, we will consider linear part of the dynamics first. And then we have to select a positive semi-definite matrix Q and solve it. And if we get R, we can find that it is positive definite. Okay. So what we can get is there exists a region around the origin in which the nonlinear system is stable. And then we can determine the region of stability of the nonlinear system. Okay. X dot equal to f of x will be stable in region v of x is less than k. So this can be found. One example was shown. We get R matrix. And if v dot of x should be less than 0, x2 is less than 1. So the region of stability is given by here. Okay, region of stability is also dependent upon the choice of Q. So it is based on trial and error basis, right? So Lyapunov stability. So in case in your exam it is told to find whether the system is Lyapunov stable or not, you have the A matrix. You just find its eigenvalues. using those eigenvalues, you can say whether the system is stable or not stable. Okay, if the eigenvalue is in the left half of the S plane, then it is stable. If the eigenvalues is not in the left half of the S plane, then the system is unstable. Okay, if any one eigenvalue is not in the left half of the S plane, that system is unstable. So we what it is said is we have x dot of t is f of x. Okay, it is f of x. Let us use capital X because it's a vector. So what they do is they linearize it. So they make it as a into x plus g of x. They write it in this form. And this A matrix they are using. And what they do is then they find using A transpose R plus R A is equal to minus Q. They select a Q first, then they find R. And then since they have to prove V dot of X is less than 0, then they, and what is my V of X? V of X is X transpose R X, right? So then they do the V dot of X and they get the expression. And then they equate the condition, it should be less than 0. So this depends on choice of Q. So depending on the choice of Q, you can get a range of stability. Okay. So this is the power of Lyapunov stability. And also you can use Routh-Hurwitz criterion and other stuff to determine if the system is stable or not. So this is for week 5. Now we'll go to week 6. Okay. So week 6 is a type of control design method, which is known as state feedback. So what do we mean by state feedback? Means we have a system. This is the 1 by S of it. This is the state X dot. This is the state X. So what is this given by? X dot is equal to your A into X plus B into U. Okay, and Y. Then you have what is known as a C and a D, and you add them, you will get your Y. This is the Y. Now, in most control systems, what is done is we, so this is on my overall, let us say, this is my overall plant. Okay, this is my overall plant. And this is represented like a linear time invariant plant is represented many times in different diagrams you would have observed. Now, usually what they do is they have your plant here, you have your Y over here, you take it, you have certain reference, you subtract it, you get an error, which you feed it to your controller, which will generate your U to drive your plant. Okay, this is known as we are like cascade compensation. But in our case, we have a plant. It has Y. What we need also is its X. And that we multiply by K. That gives us our U. Okay, and our U and minus K. So our U is equal to minus KX. This is how we do for state feedback. This is what is done for state feedback. So we already know that X dot is equal to AX plus BU. Since we are substituting U equal to minus KX, what do we get? X dot is equal to AX then minus BKX. So our x dot is equal to a minus bk into x. So this is our closed loop A matrix, and we have to place the poles, or eigenvalues of A closed loop. Okay, one more point to remember is we all before doing state feedback, you need to check for controllability. You need to check for controllability. If the system is not controllable, then you cannot do state feedback. You cannot do arbitrary pole placement. So if system is controllable, then theoretically we can achieve arbitrary pole placement is possible using state feedback. So in state feedback, what do? There's a MATLAB command which I have shown, which is place A, comma B, comma your poles, and this will give you a gain K. So what exactly you are doing is you have your A, you have your B, and these are your desired pole locations. Okay. From that, you will get your gain K. Now, how do we know what are the desired pole location? That which pole, if I place, it will give me a good response. It is like a trial and error basis, right? That I select some set of poles, I get some response, I view it. Then I find it's not good. I will again shift the poles here and there, and I'll get another set of gains K, and then I will again implement. So it is like a trial and error process. We might, through some good thumb rules, etc., we can place the poles at certain locations, but it is not always possible, right? So, how do we select those poles, and and through which we get the gains K? So, there's a next method known as LQR. Okay, before saying this, you how do you solve these things? How do you solve state feedback problems? You get your A closed loop, which is equal to A minus BK. Okay, then you get the closed loop characteristic equation, okay, which is SI minus A closed loop. Then what is your desired polynomial? That will have some form, right? This depends on your specifications, etc. You get a desired polynomial. Then you equate the coefficients. You have to equate the coefficients, and it is better when your A matrix is in controller canonical form. When your A matrix is in controller canonical form, it becomes easier to determine the gains. Mathematically, it becomes easier. Okay. So next we will go to what is week 7, which is your linear quadratic regulator. Also known as your LQR. Okay. So what do we mean by linear quadratic regulator is we have a cost function g of x transpose px plus u trans ru, which is x transpose qx, I think. x transpose qx plus u transpose ru. And this cost function has to be minimized, minus infinity to infinity into dt. So you have to minimize it. So q has to be positive semi-definite, or it can be positive semi-definite, but r should be positive definite. Yeah, and q will determine how much is the deviation of the state from your desired equilibrium point, and r will shape how much control input you are giving, right? So we can vary q and r, and through that we can place the poles. So what we get when we do use LQR is we get an algebraic Riccati equation. You get an algebraic Riccati equation. ARE. Okay, which is actually A transpose P plus PA minus PB R inverse B transpose P plus Q, this equals 0, n cross n, and we get K equal to P into K is the R inverse B transpose P. Okay, so your P, let us consider second order case, it will be P11, P12, P12, P22. Okay, this is the P matrix which you will obtain, and then you have to find the gain K. So when you will be solving this ARE, it is very difficult. So you have to make sure that this P11 is greater than 0. And this P11, P22 minus P12 square also is greater than 0. So you must select such gains. You must select such P11, P12, and P22 such that these things are satisfied. So you have to make sure P11 is greater than 0, and P11 into P22 minus P12 square is greater than 0. So all these things you have to be watchful and make sure they are satisfied. So there are various conditions, and this is very difficult. And it is difficult to solve this sum. Okay, so I hope you will proceed with caution when solving such a sum. Next, we will go to week 8. So we are going to what is known as an observer. So we did all this analysis and we have seen that state feedback is very good for us. That is, we can do arbitrary pole placement. We can use the concept of LQR, and suitably we can shape the system response, and we can reduce the deviation of the states. We can minimize or properly control, the control input and etc. But what is required is you need to observe all states. You need to measurement of all states is required. All states of the system is not practically feasible. It's not practically feasible. And why is that? Some state may not be accessible also. It is very dangerous. It may be internal and you cannot go over there. It is a hazardous environment you cannot do. Or it is very expensive. You cannot have sensor for each and everything. As though in a bread toaster, you will put a sensor to see whether the color of the bread has changed brown, or it is still, or it's become black, or it is still retaining its color. You cannot have so many sensors, right? It is not practically possible. But we have done all this theory we have developed regarding state feedback. So how do we implement state feedback for our design? So what is done is there's an observer. What an observer will do is you have your plant. Okay, it has U and it is giving you a Y. You have your observer, which is taking the same U, is taking this Y, and will generate a Y hat. What is done is Y hat minus the Y is an error which is fed back. And your observer actually generates your X hat. Okay, and this X hat is used, it generates a x hat, okay, which is used with some gain k to control your u. So instead earlier when we had u equal to minus kx, now we get u equal to minus kx hat. Okay, so for an observer, what we do is, we know our system is given by x dot is equal to ax plus bu, y equal to cx. Okay, this is the plant dynamics. So for observer, it is x hat dot is equal to a into x hat plus b into u plus l into y minus c into x hat. These are the observer's dynamics. This is like the Luenberger observer. And what is its function? Its goal is to minimize E, which is equal to your x minus x hat. So if you do that, it will come out to be A minus LC into E. So you have to place the poles of the observer in such a way that your error will be minimized and your error tends to 0 as t tends to infinity. This is what was proved for the Luenberger observer. But this depends that we know what is the A matrix, we know what is the B matrix. We are very sure of the U, we are very sure of the X. We have not considered any measurement noise, we have not considered any model dynamics. But in the practical system, these will come, this will all creep in. And when it becomes like this, when it becomes complex, what has to be done is a Kalman filter. So Kalman filter is basically a optimal state estimator. So we will look into it further. So these are the dynamics, and it is usually recommended that the observer dynamics should be at least 10 times faster than your plant dynamics, so that your estimated states are accurate. Okay, we don't want our observer to be slow. Next, that is the separation principle, that the observer dynamics must be quite fast as compared to our plant dynamics. Next is we'll go to week 9. Here, there are various techniques. So you have a plant. You have U, you have your Y. Okay. Now, we are if we have to do digital control, we have to do what is known as sampling. Okay, one case is we take uniform samples. Uniform samples of U and Y. Okay, this is a simple case and the one which is studied a lot, and it has some advantages and etc. But it also has some limitations. There are advanced techniques which Sir has introduced, which Sir has taught in this course. One is your multi-rate output control. You have a multi-rate output control. That is, your input U is sampled at a rate of T. Your output Y1 sampled at a rate of T upon N1. Your output Y2 sampled at a rate of T upon N2, and so on. It goes on changing. Okay, so what it means is you have different rates of sampling. And it was shown that there's something known as the controllability index mu. Okay. And that means your N1, N2 all should be at least greater than or equal to mu. It should be greater. Otherwise, you cannot do. That is the requirement for multi-rate output control. Similarly, there is a FOS, that is fast output sampling. Okay. And here N1 and N2 is equal to some N, which should be again greater than mu. And it is a special case of MROC. And there's a certain constraint that the poles cannot be placed at the origin for this case. And another thing which I'd like to tell, since we are dealing with digital control, poles or eigenvalues should be placed within the unit circle. Okay, the poles or eigenvalues should be placed within the unit circle. This should be taken into account. So after fast output sampling, there's another method known as POF, that is periodic output feedback. So using in POF, what happens is the output is sampled only once, and the input is updated with different gains in a cyclic periodic fashion. Okay, using the sampled output. Okay, so that is why it is pure. But the problem with this is it has discrete discontinuous inputs, and this is not always desirable. Okay. Next, we will go to week 10, where Sir has discussed about the Kalman filter. So the Kalman filter is an optimal state observer, and it minimizes the square of the error. Square of the error. Okay, so as it is minimizing the square of the error, what else? It uh, it has two steps. One is the prediction. It has a prediction stage, and then there is a correction stage. Okay, and there are two types of Kalman filters. One is the continuous time. Another is the discrete time Kalman filter. Okay, so these were studied for week 10. Next, we will go to week 11. So in week 11, basically, Sir has done what is known as a case study of a nuclear reactor. So as Sir works on these nuclear systems and nuclear power plants, and his expertise is in all this, so he has considered that case study, and what he has done is he has derived the mathematical model. He's derived a mathematical model considering various assumptions of a nuclear power plant or of a nuclear reactor. And that comes out to be a non-linear model. Okay, since the model is non-linear, what is done is we have linearized it around an operating point. Okay, after we have linearized it around an operating point, we have got some matrices A, B, C, etc. Okay, using the system parameters. What we checked is for observability and controllability. So we have this x dot is equal to ax plus bu, y is equal to cx. So x belongs to 5 cross 1. So there are 5 states. Y belongs to R2 cross 1. So there are two outputs and U belongs to R1 cross 1. So it is a single input. So it has two outputs, one input, and there are five states. Okay. So we have two outputs, one input, and five states. So it was also shown by Sir that if you observe only one output, you cannot the system is not observable. If you observe the second output alone, the system is not observable. But you have to observe all the outputs at a time so that the system will be observable. Finally, the system is observable. And also, it was proved that the system is controllable only if the nuclear flux density should be greater than zero. So it was both controllable and observable if under the condition that the nuclear flux density should be greater than zero. So this was the condition. So after that, Sir has done what is known as output feedback design. And Sir showed that only two poles could be shifted using output feedback. Okay. Next, we'll go to week 12. Week 12. So here in week 12, what Sir has done further advanced control techniques. So first, Sir used UOF control for the nuclear power plant, for the nuclear reactor. Then Sir used FOS control for the nuclear reactor. Then Sir used the Kalman filter for measurement, for correcting the measurement, or to improve the response of the sensor. Okay. So this was all considered by Sir. So Sir considered various case studies, and in the case of UF control, FOS control, what I observed, what we observed is that the gains can be different. We are doing pole placement, but we are getting different gains. So there are unique possible combinations of gains which would result in the same desired pole locations. But what we must do is we must select such a set of gains. So such a set of gains such that we are having the controller gains k of a lower magnitude, of a lower value. Otherwise, when the controller gains are very high, then any small change in the error, any small deviation, etc., will result in a drastic change in the input signal Q, and that is not always desirable. All right. So there can be various techniques such as LMI based techniques, etc., to find out the optimum gain and optimum values of those matrices and those gain vectors, etc. Okay, and the power of Kalman filter was also shown by Sir. How when my output is messy or output is slow, my measurement is slow, and using the Kalman filter, we can get it to respond to show the behavior very close to my actual system behavior. Also, what Sir has shown was the offline. So offline tuning of Q and R for the Kalman filter was demonstrated. So Sir selected one value of R equal to 1 and he kept on changing Q and he saw how the system response is changing. whether by increasing Q, whether it is accurately following, but also he observed that the certain noise is increasing. So through what is known as some certain performance indices, you can choose select different values of Q and R and train. You can train your Kalman filter on the data, measured data of your system, of your plant, and then after tuning your Kalman filter, you can actually uh, put it online, put it in the actual plant controller. Okay, you can actually implement it. All right. So, my final word will be all the best for your exams, and be careful and watchful while solving the sums. Try to avoid all those silly mistakes and errors. And you should target the simple sums first. Once you are sure that the simple sums are done, you focus on the question which you know, and you write the formula also. As this is a written test, you write formulas. You write formulas and very, very important formulas you remember, like the algebraic Riccati equation, as well as this SI minus A. How do you find the inverse of a 2 cross 2 matrix? Okay, this is very much important. Then eigenvalues and eigenvectors. Okay, these are necessary things for you to remember, which will help you to solve the sums fast. Laplace transform, partial fractions also, then there are various canonical forms, the Jordan form, etc. So there, those to be able to see the form and to represent it in the block diagram, as well as to be able to represent in the ABC matrices, etc. Those also will be useful. So directly you see the transfer function. So very important is transfer function to state space. So you must remember that formula. You must remember that from these gains go to this part of the A matrix, B matrix, C matrix, etc. So if you know that, then you don't have to derive it all over in the exam, and also you may not have time. So it is good to memorize all these things and keep it in mind. Okay, so today I conducted the summary session. We talked about the various weeks, what are the very important topics I touched upon, and various things. So you can refer to these notes for doing a brief recap, but I hope you also have your own notes and you have also taken notes for what Sir has taught, and you're while solving the assignments also you can go through the assignment problems to get an idea of what you have to do, what kind of questions might come in the exam, and these important formulas and how to solve all these things. Please note it down very, very carefully. And like controllability, observability, how for doing state feedback, you need to check if your system is controllable, observable. There are many tricky questions where it tests your understanding. So you have to read the question carefully and look at the options. You don't need to always start solving a question. If you look at the options, there are certain options which are infeasible, which are impractical, which are ridiculous. So those options, if you can eliminate, you be closer to the answer. Okay, so that's a way to look into it to try to find out. And also you'll have to use a gate calculator. So please practice using the gate calculator in the exam. Okay. And as much as possible, try solving the sums on your own without seeing the solution. So you can also refer to my notes which I have uploaded on the drive, as well as my lecture videos also are there. So you can check also where we have solved certain sums, which would be useful for you all. Give you consider state feedback, LQR, then observer-based control, then digital control, the various three types of advanced control algorithms, control techniques. So one way to remember is you can make, the overall flow chart or algorithm program. There's a busgood algorithm is there. There's the Ackermann formula is there. But I prefer to actually derive using SI minus A and A minus BK, etc. It is easier that way. Periodic output feedback also is there. Kalman filter, this, which has a prediction stage and a correction stage. The case study of the nuclear reactor also was shown by Sir, and output feedback design, POF control, FOS control, Kalman filter, etc. All these were touched upon. So all these advanced research level problems was touched and was shown to you all. So I hope you'll be able to do your exams well and pass with flying colors. Okay. So thank you again.